Hey, good afternoon, everybody. Thank you so much for coming along to our presentation today. I'm Scott Mason. I am the head of sustainability at Kooltech, and what I'd like to do today is just run through presentation with you, a little bit of a follow-on really from our roadshow series, which was really well attended throughout the UK. There is a question and answer box, which obviously you're welcome to use. So if at any point during this presentation you do have questions, please just jump in there. More than happy to field your questions. And to kick off, what I'll do is I will just share a few stats from the roadshow event, which we went on through the UK. Now, a few of you may have attended the roadshow. I can definitely see some familiar names in the list, but there may be others which didn't attend. And it might be, due to its success, actually, that we are going to be rehosting some kind of event next year. The CAHVR, which is the unit in question, which we took on our roadshow, so we took around the UK. That unit is going to be installed at a demonstration suite down in Fareham. Now, that is Fareham, but it is the South Coast, so it's very sunny here. I'm sure it's sunnier there. So if you have got an interest in seeing the unit being dismantled again or in a working environment, delivering heating and hot water, which is one of the concepts we spoke about during the roadshow, that facility will be available for our customers and sales functions, etc., to use. So if that's of interest, please register your interest and we'll see what we can do to accommodate you. So just before I kick off with the actual presentation and core and go into commercial heating and sizing and selection, I'm just going to share my screen and just run through some very quick stats with you guys for how we feel the roadshow went. As it stands, none of my colleagues have messaged me to say they can't hear me, so I'm assuming my audio is working just fine. So I'm going to continue on that basis, although I have got a track record of not unmuting myself when working on Teams, but no news is sometimes good news. I got a thumbs up. Thank you, Simon. Brilliant. That's good. All right. So the roadshow itself. So we kicked off in London at the Hilton at Tower Bridge, and it was a fantastic event. It was the first time we'd really done a roadshow, so we were thrilled with the attendance. We got 80 engineers throughout the day, and we got about 47 engineers from the Young Engineers Network community in the evening. So a good education experience for all. And by this point, our Chavar had travelled about 92 miles. So the unit made its way all the way to London, delivered for the first time. This is probably the best travelled CAHVR in the country. The unit then made its way down to up to Manchester. So in Manchester, very similar concept. We followed the same routine, same level of attendees, really pleased with how it played out. And the actual event itself at this one, it was quite special because, like I said, it was our first sort of roadshow event. We were doing CPD seminars previously. You know, people sort of understood the content. But the main thing was the experience it gave people sort of being with the unit itself. So if you do get the opportunity to come down to Fareham to see it, I definitely would say to do so. Or certainly look out for our roadshows next year. Someone actually described it as being given experience, which was just a lovely thing to hear. Number three, it then made its way up to Glasgow and Edinburgh. The presentation was actually in Edinburgh. The previous day, though, we just had an event in Glasgow. Because of its success, we're likely to be hosting another event in Glasgow at the end of the year for the CIHBR, for those that didn't attend because it was on the other side of the country, I suppose. But again, fantastic attendance levels. And by the end of it, we'd reached out to over 320 engineers. So we were really, really pleased with it. And thank you all so much for your support. And for anyone out there thinking, about this fantastic animation, did Scott put that together himself? Yeah, I put it together myself, and it took way too long, but I'm pleased with it, just like the actual roadshow itself. So that's our brief interlude, and now I'm going to dive into actual content. And I think that interlude served well because a few people did join while I've been talking anyway. So the presentation I'm going to deliver for you today is basically going to be the core content from the roadshow itself, but then I'm going to dive a little bit more into the sizing and selection sides, try and give you some insight to the unit's operation and function and how it looks without physically having it with you. But it just felt like a good opportunity because the roadshow did get such nice feedback that it would be great to sort of extend this out, reach out to more people, and hopefully continue positively influencing how this product's applied and help people with their decarbonisation journeys ultimately. So today we're talking about primarily retrofitting products. That was what the roadshow was centered around. And the first thing I like to touch on when delivering these presentations is basically a little bit about the reason why air source heat pumps are becoming, well, becoming so popular, but why they are so popular, why they're so mainstream now. What we have on the screen at the moment on the left-hand side is different fuel types. Hopefully you can see my mouse. Hopefully it's giving you quite a smooth. I'll slow down so it's nice and smooth and not too laggy. But what we have is the kilograms of CO2 for each energy source published, and this is from the NCM modelling guides. This is the national calculation methodology for carbon emissions from different fuel sources. With that, what accompanies it is the kilowatt hours PE value. Now that's our primary energy, and the primary energy is important because that's your true carbon cost, really, if you will. That's going to take into account things like transmission losses and whatnot. So things that are associated with the fuel beyond being burnt at source. Electricity is a little bit different to any other energy source, and it's because when you look at it, you've got January through to December published, and January through to December, the kilograms of CO2 for each kilowatt hour fluctuates, and it fluctuates reasonably wildly. You know, we've got 0.1 versus 0.16. You know, it's quite a big difference, you know, about 30% hike. And the reason for that is in the summer, you know, longer daylight hours, lovely sunny days like today. And as a result, the renewables infrastructure in the UK obviously generates better. So we're less reliant on things like fossil fuels at this point. What I do have is a little app that's a nice app just to download. It's run by a university, not me, but it's just called UK Grid Carbon. And it gives you the UK's grid carbon intensity at this exact point in time. So it tells you where our energy is coming from. So looking outside, really sunny day in the North Cotswolds. And at this point in time, 28% of our energy is actually coming from solar. That's a big chunk of the UK's energy right now. The next 25% is, of course, coming from gas, which still is a major contributor. But long sunny days, 9.2 megawatts being contributed by solar. The grid's carbon intensity at this exact point in time is 148 grams of CO2 for each kilowatt hour. Now, that kind of makes sense, and actually, in line with these projections here, lands pretty perfectly for a June day. So that's might be a little bit of a fluke, really, but it's just nice that that happened for me right now. But what you'll also notice is your primary energy also has a swing. The primary energy factor comes down during the summer, and that's largely because electricity is not a great thing to distribute, as you all know. You know, the high voltage power lines, etc. You get a bit of a pressure drop through there, or a transmission loss would probably be a more appropriate term, and as a result, you lose power. So the primary energy factor is quite significant, but the PV arrays are usually a bit near to the big conurbations, which is where the energy intensity map would glow and show you where the energy is actually going. So as a result, also comes down. So you get like this double summer benefit. So what we've done is just very quickly just go through some very quick maths for you. A gas-fired water heater delivering 1,000 litres of hot water in an hour. That's going to take about 58 kilowatts. Or if we could forget the hour bit, it's just going to be 58 kilowatt hours of energy. And at 58 kilowatt hours, primary energy factor, carbon intensity of the energy source, product efficiency, total emissions as a result of basically generating that 1,000 litres at 60 degrees centigrade. Sorry if you're getting any background noise, by the way. I live in quite a rural location. I've currently got a tractor driving past my window very slowly because it's obviously doing some topping or something. So gas, energy intensive, financially, at this point in time, unfortunately, probably the most competitive source we could use for generating hot water. But there is a lot happening in that space from the energy suppliers to address that. And there's lots of newer tariffs coming out. And also we're doing a lot with the actual technology to make it more efficient to bridge that cost. We can get, you know, a parity in running costs now. And the parity in running costs is great, but a parity in running costs doesn't necessarily offset the initial investment. So from a retrofit point of view, a lot of what we're seeing is going to be like public sector decarbonisation funded projects. It's going to be PSDS, probably phase 3, C, whatever. So these are the things that are coming through. And then if we look at an air source heat pump, now I've taken a coefficient of performance, which is a COP of 1.6. Now the reason I've taken 1.6 is because that's what the unit, the CAHVR efficiency will be at an outside air temperature of -2 degrees centigrade and a flow temperature of 65. So it's potable hot water. We need to store it over 60. So realistically, I need to deliver 65 because there's going to be a plate heat exchanger or a coil or something in there for our heat transfer. It'll be a plate heat exchanger. I don't know why I say coil. It's very unlikely to be a coil. And at -2, flow of 65, our efficiency is 1.6. So from a carbon emission rate, significant saving. from a financial situation at that point in time, it would be more expensive to run than the gas equivalent, unfortunately, depending on your energy tariffs and how that's made up and whether you've got any on-site generation, of course, because if you're generating electric on-site and you're using it on-site, that is the main way you can get a decent saving from applying electric technology. So what we have on the screen now is called a coefficient of performance. That's your 1:3 ratio here, which is 1 kilowatt in, 3 kilowatts out. Now, what we saw, though, was that actually at different points in time, and we'll look at this in some more detail shortly, that 1.6 value that we saw before, obviously that's not a 1:3 ratio, and that's because when people publish coefficients of performance, they generally publish them at 55 degrees centigrade, and also with an outside air temperature of 7, which is close to, but not quite, the UK average temperature. So as a result, yeah, my copper 1.3 sounds great, but it's kind of a fictitious thing. If you're looking at decarbonising a building, what you're really going to be looking at is the seasonal coefficient of performance. That's your SCOP. And that takes into account different flow temperatures for that heating circuit, or a fixed figure of 55, 45, or 35, depending if it's a high, intermediate, or low temperature SCOP. And it'll also take into account different outside air temperatures through the course of the year. Now, that's important because that means that the efficiency value is going to be real. And when it comes to type of application, well, really, these units, this sort of technology can fit in anywhere. There's barriers to use, don't get me wrong, but that's what we're here for, to try and help you overcome. And those barriers, generally, we find when we're looking at retrofit, existing electrical infrastructure, that can be a big one. If you've not got the power available, you've not got the power available. So what we do in those circumstances is we look at different methods of application. You can either increase the energy infrastructure, which would obviously allow you to go fully electric, which is great, or we can work out, how much energy we actually have. As a result, the air source heat pump can be this size, which means over the course of the year, we're looking at a contribution of 75% from the air source heat pump technology, because actually that peak load, the final 10% of operation is probably about 30–40% of your actual heat load for the building, because it just is those days where you need the heat and you need that top up. So then we look at bivalent applications and things like this. But even on a bivalent system, you can get very solid carbon savings. So it depends what the drivers are for the job. The other barrier is going to be things like noise. So the Chavar, it doesn't really have much positive pressure coming off the fan outlet, something like 10 pascals. So as a result, it's really, really quiet. However, if I was in a hotel trying to sleep, would I want one outside my window? Maybe not. So actually, again, there's different levels, and me saying something's quiet, well, quiet doesn't really mean anything, does it? A whisper can be quiet, but so can a shout if you're in an open field. So realistically, again, this is a job-by-job metric, and all of those decibel values can be published, and we've got availability for all of that. So as you're doing your analysis to work out whether the siting is appropriate, we would support that process just with site-specific data. What's the other barriers going to be? Well, the other barrier is probably going to be flow temperature. So your historic retrofit, realistically, you've got a boiler working on 80–60. We want to flow at 80 degrees to the building. We want to return at 60 degrees. We've got a 20-degree delta T across the building. Boilers are comfortable doing that. It won't condense, but it doesn't really matter if it's an existing system. It does matter from a carbon point of view, of course it does. But on older buildings, if it's not condensing, it just means that your efficiency is lower and your gas running cost is slightly higher. Later buildings went to 70–50, so they got underneath that condensing boundary, but even then 70 is a stretch for most technology, which we'll discover very shortly. And then one thing just to talk about as well before I talk, this is a pro heat pump presentation, by the way. I'm sounding very negative so far. But one thing as well to consider on your retrofit application, because basically the key to a good presentation is that actually we end up all having a really good experience when applying this technology, and we're open, as open as possible with the pros and cons of what might be encountered. Because not everything's always going to be perfect, and actually you need to appreciate that up front, because if you go into this thinking, I can retrofit with an air source heat pump at 80 degrees and my running costs are going to come down and I'm not going to have space problems and blah, 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 then actually we're probably setting ourselves up for a less than perfect experience. We want to make sure things run smoothly, I suppose, is the purpose here. It's not me saying negative things, it's considerations. So when we look at the fabric of a building, so why is this important? Well, I mean, I can retrofit any building with an air source heat pump, really. If I make my emitters bigger or I take into account different things that allow me to distribute that power. But what air source heat pumps do is generally, on a well-designed system, will run at a lower flow temperature. The new CIBSE guidance will state that flows of 55 degrees is probably very sensible, and that that this is this is what we should be aiming for. Of course we should, because the overall system efficiency goes up as a result, but it's also not always possible. However, if you increase your emitter size and you flow at 50 degrees centigrade, but then previously you had a smaller emitter and you had 80 degrees into it, because it was a higher temperature, the room's subjected to a stronger convection current, so you move more air. And when you move more air, what you do is you hide things, and you hide things like drafts falling off single panel windows. For example, air source heat pump at 50 degrees or a 35-degree underfloor heating circuit wouldn't have that same air movement effect. So actually drafts coming under doors, etc. The things that people are going to notice more than anything, despite all of these things obviously being things you should consider and do, the thing that's going to bother people is whether or not they're comfortable in that environment. Energy use is almost incredibly important, but obviously secondary at that point when it comes to user experience, because a user who, we could decarbonize a building massively, but if they're now uncomfortable in that immediate environment because they can feel a draft under a door and cold air falling off of the window at them, well, we've actually probably not done the perfect thing for that environment. There was other considerations that should have been in place. And they're the things that will get you complaints afterwards, really. But the benefits for why you reduce before you produce, well, they're pretty obvious. Lower energy bills, lower initial, meaningful fabric upgrades can sometimes be very expensive. However, if you can make fabric upgrades and it has a good impact on the heat load of the building, that might bring you down a size of air source heat pump, and a size of air source heat pump can translate to tens of thousands of pounds, or it might even make a job possible actually, because that might bring it within that value you've got with residual electricity or whatever. So big considerations: reduce that heat load as much as possible, or as much is practical for your environment. And some useful documents that I think would be worth consulting. The MCS, the Heat Pump Design Standard. So if you've worked on projects in the past that drove the renewable heat incentive, for example, this prescribes a lot of the information, like outside design conditions and things you'd be taking into account when designing an air source heat pump application. That's sort of up to 40 kilowatts, the old MCS stuff. But a lot of the information translates and is relevant. AM17, large non-domestic buildings. This is definitely worth a read, and actually very graphical as well and easy to digest. So kudos to Sibsy for this document here. And then Letty as well do a lot of good work. So Letty make things very, very easy to digest and understand, and very palatable. So check out the Letty website. That's the London Energy Transformation Initiative. Lots of the principles and things that they set out there are obviously translatable throughout the whole of the UK and not just central London. It just is good, clever guidance. So this brings us on to, now we've done a bit of groundwork, the selection and sizing process. So the things to consider when applying an air source heat pump to your building. It's going to be focused on the Chavar, because of course that was the unit that accompanied us on the roadshow. But basically, what we're going to do is we're just going to run a size and selection for a project, really. It's going to be a small commercial heating and hot water solution, and we're going to look at some schematics of how we can address this scenario. So first consideration, when we're running a selection, and I'm going to do a live demo as well, so don't worry if this doesn't all just land straight away, but the first thing which we're going to have to take into account when we're working on an application for a building is going to be our outside design temperature. And the reason for that is the outside design temperature directly translates to a product's efficiency and kilowatt rating at that point in time. And the reason that's important is, again, because we've got, and you'll see this again, sorry, you'll see it in a moment. We've got products in our range, which in the south of the UK, I would describe as a hot water product. So it can do heat or it can do hot water. And that's because it can deliver 65 degrees centigrade at these design ambients. So I can make potable hot water. But then we've got but then when you get down to like -5, for example, so our colleagues up in Scotland, they would use that product significantly less for hot water because we can't get over 60 degrees. So if we do use it for hot water, we have to incorporate things like pasteurization regimes, etc. And actually, there's probably better products suited at that point in time. So the outside design temperature changes significantly what products in our range are actually available at that point in time. And generally as well, one thing which is a bit of a shame, and we're going to look at embodied carbon in a bit, and we're going to look at refrigerants in a bit, but generally, the lower the GWP, or the global warming potential of a refrigerant, the harder it is to compress. And as a result, the lower the flow temperature you would achieve, which is a little bit of a shame, really. I don't fully understand the science behind that, unfortunately. I'm not a scientist. but I do know how it impacts the actual product. So as a result, it just means that product selections really need to be a job by job thing, and they're fitted to drivers. One of the things I would say as well is, if you phoned me in my previous life and you said, oh, I'm replacing a boiler, I need 60 kilowatts and it needs to be on the wall. That's super transactional. It's quite easy. Here's 60 kilowatts of boiler. This is my quotation. This is the product spec. With air source heat pumps, there's quite a few questions to get to the bottom of before we can get to that point. It's not as easy as just saying, yeah, cool, here's 60 kilowatts of heat pump. Unfortunately, there's a lot of like different drivers and things for projects that affect the selection, and it's about making the best selection with what's available. And unfortunately, there is no one size fits all. The Chabar, to be fair to it, does go some way to addressing that, just because it has got such a robust operating window and it's very efficient. But again, we're limited to a single size and it's modular. So when you're up at sort of 500 kilowatts, would I offer 12 of those, or would we be looking at maybe one of our Climate Bonita ranges and doing it in 3 lots of 50%, for example, because the capex argument will be totally different. Again, very job by job, but this is what we're here for and why we have these discussions on a project basis. What you have on the screen now is quite a cool chart, and this is a bunch of our popular products along the top of the screen. So the CAHV, this is like our sort of mainstream market leading unit. This is the Mitsubishi CAHV unit. Generally 40 kilowatts, but the kilowatt rating does drop off at lower ambience slightly. So when you get down towards -5, you're sort of closer to maybe 35 kilowatts rather than 40. But at 0, you're closer to 40 rather than 35. So the output is affected. Anything sort of above sort of 2-3 degrees is almost a constant 40 kilowatts for this unit. And its operating window looks like this. So this blue window, what I have is on the left-hand side, 0 to 80 degrees centigrade as a flow temperature that the unit's capable of. So this unit can flow at up to 70 degrees centigrade or 65 at -20. Now that's a hell of it. That is a real achievement, to be fair, and this will make more sense in a moment. But this operating window is super robust. So whether the outside air temperature is 0 or +30 degrees centigrade, I can give you 70 degrees. As long as what you're doing for your building lands in this building profile, this unit will generate you the heat to make it happen. On a big kilowatt rated system, would you want 20 of these? Maybe not. So again, consideration for a site. However, on a light to medium commercial project, this is why these units are so popular. The next unit we have in our range, which is our next most popular unit, is actually a Climate Bonita product. And Mitsubishi own Climate Bonita. And the Climate Bonita unit is manufactured in Italy by Climate Bonita. It's called the NXN or the NX2N. It's just basically 2 of the same range, but one of them's larger with a second fridge circuit. And the operating window looks like this. So believe it or not, this is still a robust operating window, but it's a totally different scale of performance. Look, so I can give you 55 degrees down to a temperature of +7. So realistically, at your design condition, this is a unit that can produce 50 degrees of heat. So you would need a heating circuit underneath 50 degrees centigrade. If you said it was potable hot water, this would be a preheat only, because I'm not going to be able to give you that 60 that you need. If you don't want 60, absolutely fine, but then obviously you just need to do the relevant pasteurization regimes and whatnot. And actually distributing at 50 probably is a little bit low on a potable store system, because you want to be returning at 50 really. So generally when we see hot water sort of at lower temperatures, it's more 55, and then we top up and pasteurize rather than sort of being down at the 50s. It's just that little bit too low, But this unit, if it's on a heating circuit, is better suited than the Chav generally, because I can build my circulating pump in, I can flow at 50 degrees all the time anyway, so actually it'll do heating. My performance curve probably is going to be weather compensated and looks a little bit like this. So the Chav will do it, but it's at the lower end of the operating window. The NXN will definitely do it, and it's banging its operating window. So a funny thing about air source heat pumps is they kind of have like comfort zones, and you can almost make an accurate prediction of the efficiency of that unit and how well it's going to work and how long the compressors are going to last based on how your performance curve lands in the profile. So do you see how like the Chavar, that 50-degree curve is at the bottom of its operating curve, whereas for this, it sort of scales the operating curve. So the impact is, I can, without even doing the maths, I can almost with certainty say to you, the Chavar's efficiency at the lower flow conditions will be equal to or worse than the NXN's. Whereas if it was a high constant 50 degrees centigrade flow rate, that's bang in the middle of our chav's operating curve. So actually, the chav hour is going to give us probably an overall slightly better system efficiency at that point in time. So comfort zones are important. That also translates to longevity. The next unit to look at is the E series. Very, very popular, but a different animal again. So 55 degrees, quite a robust operating window. You can see it's very squared off. It's quite artificial. You know, it's been designed to do certain temperatures for a reason. Then the next one to look at is probably the AWHT. Now, the AWHT was a very popular unit, but it's not so popular now. And it's got a great operating window. But why is it not quite so robust, you may ask? Sorry, quite as popular as it used to be, you may ask? Well, it's R410A. So we don't lead with this unit anymore. So the AWHT was brilliant in its day. It still is there and it's still available and it still works. However, from a global warming potential point of view, the refrigerant's probably not the best because actually the sizes I can match on a modular basis with the CAHVR. So the right thing to do is lead with the CAHVR because the CAHVR has a global warming potential of its refrigerant of 148 and the AWHT sits closer to 2000. So it's a totally different thing when it comes to environmental impact from the refrigerant choice. But you see what I mean about, you know, this is quite a basic unit. It's going to produce your heat, but because it's a high GWP refrigerant, it's actually got quite a good operating window when compared to low GWP alternatives. In fact, it's the second best, if you will. So big consideration for that. We're always going to want to make sure that whatever your building is doing, the curve lands within an operating window for a unit. Which then brings us on to how we run a selection for a CAHVR. So this application that we're looking at is a 30 kilowatt heating and hot water selection, right? So what I'm going to do is, you should still be able to see my screen. I'm going to show you a little bit about how we size and select. So these are all of the tools that we basically run and operate in-house to almost give you like a little bit of insight into what we're sort of doing in the background and why we're asking these questions, but also how we make sure that you're going to have the, you know, sort of best experience and the system's going to work. So the first thing we start with, and this will accompany any projects we ever send you, is the TechSub tool. And the TechSub tool is a really, really wonderful thing. It's basically a series of inputs that comes up with a site-specific series of data related to the performance of my product at a point in time. And the main things for this are going to be, what is my outside design temperature? Well, I'm designing to -2 because I'm in London. Brilliant. That ties in with what we looked at earlier. I know it's doing heat and hot water, so I'm going to flow at 65 degrees centigrade. We want to protect it in the winter, so we're going to incorporate glycol. Glycol, of course, has a different, what's the word I'm looking for? Density, probably looking for density, different density to water. So obviously the kilowatt rating is impacted by the integration of glycol. Food grade glycol, unfortunately, isn't as protective as non-food grade glycol. So if you want to go environmentally beneficial and go for propylene, then actually we can protect you to -5 at 25%. If you want to go ethylene, which is not quite as environmentally a good choice, but it will protect me to -7. So again, site-specific questions. How many kilowatts do I need? Well, I need 28. And then with that, what it does is it runs a load of science for me and kicks me out a really lovely report. And then my report, which I will share with you, looks like this. And what this report does is it accompanies our quotation so that you can look back and you can understand, you know, the product selection criteria at the time and why we did it and why. It will give you site-specific information, like what's my efficiency at my design condition, how many kilowatts am I actually going to deliver at my design condition, how many controllers I need, etc., which we'll look on the quotation tools shortly. And it also gives you things which are going to be incredibly important to the unit's application, such as my unit is a 40 kilowatt heat pump generally. That means I need 1.9 litres a second. And if I need 1.9 litres a second, that translates to a 5-degree delta T. That means I'm flowing at 65 and I'm returning at 60. Now, the reason that's important is because what happens with a 1.9 litre a second flow rate is your unit's pipe size is going to be recommended at least 2 inch. So a 40 kilowatt wall hung boiler would be probably 1 inch pipe work, unless you've got an excessive run. With a commercial heat pump delivering the same thing, we've doubled our pipe work size. But doubling the pipework size doesn't just double the cost, you know, that's a lot of additional material on site, maybe slightly more specialized tooling. When I get up to 4 or 5 of these units, I might be at 100 mil pipe. It's a different thing. So it's just worth considering that flow rate is going to have an impact on your pipe size. And the pipe size is going to have an impact on your pressure drop. Your pressure drop of the unit is also going to be prescribed so that you can make sure that the pumps and stuff that we use are going to be circulated appropriately. It gives you a load of nice tech clauses, things you would expect to see, and it will also give you some indicative drawings and, crucially, that all-important operating window. So if you say to me, I want this unit to work at 75 degrees in the depths of winter, I'm really sorry, but the answer just is no. We're not delivering 75 degrees for you from this bit of technology, because that's what the operating window does say. So you've got your technical pack of information, so you can overlay that with your site conditions, make sure it's all going to function. The data books and manuals do give you additional info as well. So what we get a lot of the time, of course, is I'm working on a very specific project. I need the efficiency at this point in time, this point in time, and this point in time, because I want to work out my overall system efficiency over the course of the year so I can project my carbon savings more effectively. Absolutely fine. Of course, we've got that data. We'll run the simulations for you and we'll tell you those point in time efficiencies so that you can go and overlay it with your building profile and make the most of an accurate decarbonisation study, if you will, rather than just using SCOPs. But from an early stage, SCOPs aren't a bad choice. So we take that information, we've run our tech subtool, we've got something to accompany the quotation, which is absolutely fantastic. And then what we're then going to do is we're going to send you our indicative, well, not indicative, it's more sort of stage 3 sort of stuff. It just needs to be made more site specific. But generally, on a chavar doing heating and hot water with 1 cylinder and 1 unit and 1 hot water tank, this is pretty much what you would be doing if you were making a combined application. So we've got our chavar over on the left-hand side. That has its 54mm pipework. We flow through an air separator. These valves are just going to be arranged, obviously, in line with the manufacturing warranty conditions, etc. Generally into a 3-port valve, into our heating circuit at, say, 40 degrees centigrade. We return to our chavar, and that's going to work on 40-35 for argument's sake. And then what we do is we have a sensor inside a hot water tank that cools for heat. When it cools for heat, it closes 2 contacts inside the chavar. Those contacts are tapping T1 and 3, and it's specific on the board. That jumps the chavar up to 65 degrees centigrade. It flows at 65. The 3-port valve changes position. It flows into 1 of 2 plate heat exchangers, or 1 plate heat exchanger if you don't need a second point of failure. The second point of failure is probably a bit unnecessary on a 1-to-1 ratio thing anyway. Produces hot water, gets us back up to 60, returns via a volumizer, and then clicks back to our original position and serves heat in. So quite a traditional setup, heating and hot water. Some people like this arrangement, some people don't. Again, site specific, budget constraints, etc., etc. 3-port valves, sometimes, you know, they're a mechanical thing. They'll only turn so many times. So if that fails, obviously you'll end up with either a cold hot water tank or a hot heating tank. So a consideration to make. But it just means you've got a fault on an item that needs replacing. Sometimes people don't like the idea of the heating circuit being diverted away for a long period of time because it's going into hot water mode quite frequently, which is also fair. So site-specific considerations. If you wanted to break out the system and just have a system for each, you would do something like this. So a heating arrangement is going to be way more simplified. We've got the chav serving a thermal storage vessel and returning. So you can see we're flowing into the thermal store. The thermal store will have 2-inch tap-ins on it because that's our line size. So we don't want to end up with like a load of noise and turbulence and whatever in the vessel. That then goes off to our heating circuit, does what it needs to do, and the return will be a slightly lower temperature. Your possible hot water application is going to look something like this. So if you went dedicated hot water, very similar, but we're serving a plate heat exchanger to produce our potable hot water. That then goes into a hot water tank. And the return, again, is via this volumizer. Now, what's the point in a volumizer, you ask? Well, the reason we have a volumizer is basically because if this unit is serving hot water and that vessel is very closely sized to the building's peak flow rate or flow, then what could happen is we could have a load of cold water flood into this hot water tank. And that whole vessel, if it was undersized, could get, theoretically, to the mains feed temperature of 10 degrees. Now, let's say that's 10 degrees. Well, one, you're getting complaints anyway because everyone's getting cold water coming out the hot tap. So that's an issue in its own right. But let's just park that for a second. But if that vessel theoretically was sat at 10 degrees, the return to our plate would be 10 degrees. But then that air source heat pump might think to itself, oh, been operating for a long period of time. It's 4 degrees outside air temperature. It's pretty humid. My refrigerant volume's under freezing. I'm getting ice formation on my evaporator grill. Well, if I'm getting ice formation, I'm going to get a reduced efficiency because I've created an insulating barrier between the outside air temperature and my refrigerant that I want to transfer to. So I'm going to go into defrost for a bit. But then if that goes into defrost, but that's 10 degrees, there's no energy in the system to create an efficient defrost process. So if there's no energy in the system for an efficient defrost process, what's going to happen is that's going to say, well, I'm going to wait and I'm going to defrost naturally. Well, if you're in the middle of winter and that's frozen, it's only a few degrees outside, that could be a pretty long wait. So the volumizer is basically just that resilience in terms of storage volume. That means the primary loop's not going to drop in temperature sharply. And if it's not going to drop in temperature sharply, you've gotten rid of that risk of the defrost process, unless for some reason you've got a hot tap which is permanently open, stripping out and exceeding everything this unit is capable of delivering. But that would be a very specific process, in which case it's a site-specific thing, and we'd be looking at a totally different style of application. So you would get your schematic, and what you'd also get, of course, is your suite of complementary materials that are going to work with that. So what we would do is we would go onto our selection program, and we would send you through a load of technical items. Remember, we're a company that's owned by Wolseley. We're a part of the Wolseley family. We're a merchant at our core, although a very, very specialized one. We're a very unique style of distributor. We have massive exposure to the market in terms of suppliers and things that we can provide. So with that, if we were to transfer what we're doing here over to what we actually supply on a project by project basis, we try and make it as comprehensive as possible. So basically, other than plumbing fittings, we would make sure that your quotation includes that, and it would be specified to a point that you can obviously then do due diligence and increase your pump size or reduce your pump size or whatever. But it's all about simplification. They're a modular unit, so we're quite modular in our application and design. We internally joke it's the 80%, because 80% of jobs it does land with. But then there's always those outliers where someone wants to do something a little bit weird or wonderful, or there's some quirks to the site. And that's what we've got the applied team up in Glasgow for, to basically make sure that we can help everyone with every project. And that's why we have specialists in these spaces. Which brings us on to the next slide for our presentation, which talks about thermal stores in a little bit more detail. Now, the reason thermal stores are also super important beyond just defrost and compressor inertia, I've just had a little reminder pop up that England played Denmark. That's cool. Is basically, a lot of the time, people don't want to work on a 5-degree delta T. Well, unfortunately, the heat pump kind of has to. It will work between 5 and 10, and that's fine. But if you design at 10 and it gets to site and it's 11, it's off. So design at 5, and if we need to press the up button, we can, right? Whereas what you want to do is design to 5, primary loop, into the thermal storage vessel, 40, 35 for argument's sake, because that's our heating circuit. And then because we've got this thermal break in place, which is the thermal store in its own right, it gives us flexibility on the secondary side. So if you want to have a wider delta T on the secondary side of that thermal store, you're absolutely welcome to. But the wider the delta T gets, the bigger this volume needs to be. And also that return tapping, probably a good idea. What we'll do, we'll manufacture the cylinder so that basically it's a little bit higher up, so it hangs around in the tank longer, rather than having it shoot straight across at a low temperature and go into the heat pump and return at a low temperature. But yeah, you can have a wider delta T on the secondary. That's absolutely fine, and that can obviously have a big impact when retrofitting, if trying to use some areas of existing infrastructure. Now, the alternative methods that we look at a lot of the time as well, and again, this is job specific and site by site, but if you wanted to, we can shave some capex out of a project, or we can save space on a project by using more domestic units. So I could give you 4 14 kilowatt eco dams. I can serve a thermal store at 55 degrees centigrade, and I can produce potable hot water and serve a heating zone off the secondary side. Really nice solution, works very efficiently. However, our heating circuit originally was going to be 40, 35. We're now producing 55 when we don't need to. So our overall system efficiency has probably come down slightly. And someone's now got to wire in 4 units with 4 circulating pumps, which means that basically we now need 8 penetrations to the building, whereas previously we only needed 2, albeit the pipework diameter will still be 2-inch on the common sections. So that's one way of doing it when capex or space are the major driver, but obviously the operational carbon as a result of this goes up slightly, and so does the embodied carbon actually, because these units, although the embodied carbon in transportation is lower and stuff, there are 32, which is about a GWP of 600, whereas the CAHVR is a 454C, so GWP of 148, and the charge volume will be less than 4 of these added together. So again, site-by-site considerations, this is what we're here for to talk about, but that's, so it's pretty much what we do. That's a more detailed version which shows how you would actually apply that application and how all the controls philosophy and everything works. And these drawings are obviously available. So if anyone has a project like this, then obviously just reach out and we can make this happen. One of the reasons people also like this style of arrangement as well sometimes is because indirect vessels with pasteurization regime, they, you can have multiple points of failure, you can increase your volumes, you can do loads of good things with our range of indirects. But it just means there's some external considerations to make that can't be controlled by the heat pump. So these units don't really know those vessels are there, right? So they can't actually pasteurize it from the heat pump's controller. This is basically the heat pump's doing a heating system, and then the heat zone is a coil. So although we're producing hot water, the heat pumps aren't in control of the hot water's destiny. So pasteurization has to be handled external to the actual unit itself, for example. So yeah, we gained a lot of stuff, but we also lost a lot of stuff. So this is the side-by-side thing that I keep sort of referencing, I guess. But this is all a part of the dialogue because unfortunately there's just so many ways to skin a cat, I guess. And then what we also have a lot of the time is high temperature applications, and it's lower is obviously better because of the efficiency ratings associated with it. But sometimes this is what's needed just to make a job possible, because it might be that actually you just can't get into the building and you want to make the building electric, you want to go all electric, but we can't get into the building in a meaningful way to drop our flow temperatures. So I still need 78 degrees centigrade. Okay, well, that's absolutely fine. So if that's the case, what we do is we take an air source heat pump into a thermal store, 4540. That thermal store serves one of our EWHTs, which is a water source heat pump. These will probably both be climate bonita units at this point in time. And we can take that 4540 up to 78 degrees centigrade, which means you can serve your existing circuits. And that's fantastic that we can serve our existing circuits. However, I have doubled up on plant, so there's obviously a capex cost to that. And my overall operational carbon value is going to be so my operational efficiency of the Chav system we looked at earlier was about 310% averaging out. The Eco Dans were close to like 290. This is going to be closer to like 200. So we've made the job possible. We've electrified. We've created 80 degrees. But we've lost 100% off of our operational efficiency of that project. So yes, I've electrified, but the operational carbon as a result is higher, although still significantly better than the existing oil boiler we're replacing, or whatever it may be, Which brings us briefly onto embodied carbon, because this is always something to touch on, because it is quite important. And even in retrofit, where it doesn't have to be at the forefront of our minds, it certainly should be. So the older Chav unit, the CAHV, it was a really lovely unit, and it was like market leading for a very long time, and it really did, set the standard for air source heat pumps in this country. But the unit used a 407C refrigerant. So because it used a 407C, the global warming potential of that refrigerant was only a little bit better than 410A. So it's 1,774. And in its day, that didn't sound high. 410A was 2,000. This is 1,700. That was just the number. The unit that's replaced it, the Chav R, which is now our new workhorse that we've been supplying for a very long time now, actually, but it's a 454C, but you can see the impact that has. The embodied carbon is less than 50% of its predecessor's embodied carbon, and the reason is almost solely down to the refrigerant, because this teal section is the embodied carbon with refrigerant leakage. The orange darker section here is with refrigerant leakage. So historically, more than 50% of the embodied carbon of my commercial heat pump was in a refrigerant. It's a big number. Now it's less than 10%. So massive difference. And then that brings us on to the Quab. So the Quab is a hot water only unit. Where we've got an application which is heating and hot water and the two are separated out, we always lead with the Quab for hot water. And the reason is CO2 units need a cold return temperature. On a hot water application, I can guarantee a cold return temperature because my cold feed is going to come in at 10 degrees centigrade. So what a lovely way to use it and apply it. So if I've got a low temperature coming into my quav and a hot flow temperature in excess of 60, because CO2 works weirdly. My chavs works on a 5 degree delta T. My quav's like closer to 60. So I flow in at 10, I flow out at 70, I produce hot water at 65 degrees, which is awesome. And I've got an efficiency in excess of 300%, which is absolutely killer, way higher than any other bit of technology. However, if my return temperature goes above 30 degrees centigrade, my efficiency takes a nosedive, which means my kilowatt rating does as well, which is why we only use it and market it for hot water applications, because if you can't get that return under 30, unfortunately, the operational carbon values just don't stack up. But the embodied carbon, your refrigerant DWP, is 1. So on a hot water application, not only can we enhance the operational carbon and enhance the system efficiency and the embedded carbon, we can also make the application easier. And that's because, remember, we've got a 50-degree delta T, not a 5. So I'm using 1-inch pipework. So yeah, there's a lot of benefits to this little unit, which is why if you had a heating circuit, we try and lead with chav. If you've got hot water, we lead with clav. And if you've got combined, it's a chav doing that combined application. If you've got any other number of applications or larger systems or whatever, then of course we look at the Climate Vinita range of products and we look at all those different operating windows that we looked at earlier. Again, site by site specific conversations, but that's what your regional sales managers are for. So you've just listened to me talk for quite a period of time. It is still very sunny outside, and I appreciate you guys jumping on. I think that was a little bit of insight to what we did during the road shows, but obviously we had the physical unit there, so I'm sorry I can't show you that today. But hopefully the road shows will be coming again to an area near you. So if that was enjoyable and it's something you want to hear more about, please reach out. My details are on the screen. I can get you in contact with your local sales manager who'll be able to sort of coordinate this stuff for you. So thank you all very much.